Well, welcome everybody. For those of you who don't know me, I'm Samuel Singer. I'm the founder and executive director of Wyoming Stargazing. With us tonight is Mike Adler. You can't see Mike right now because he's out at his observatory. So that black little box that says Michael Adler is where he is right now. And he's got a wonderful picture of the moon for us with a video camera attached to his 12-inch telescope, I think. And oh, we just lost that picture, Mike. Hopefully Mike will get that back up for us for a second, and then he can tell us a little bit about what we're looking at. I know the
yeah, okay, so let's see here. Okay, can you see that now, Sam? Samuel?
Yeah, now it's back up. Thanks, Mike. So yeah, we've got.
Okay, fair enough. Yeah, this is what's.
Yeah, your voice isn't coming through, Mike. I'll give the intro here, and then when you get back in your house, once we start using the other telescope, you can fill in the blanks.
Yeah.
So the internet reception isn't great out at Mike's observatory. It's good enough, but his voice isn't coming through very well. So we're going to be looking at images through two different telescopes tonight. One telescope is going to be showing us the moon exclusively, and we're starting with that because the moon is both the brightest and the closest thing in the sky. And so we're looking at a more or less real-time image right now through a video recorder through Mike's 12-inch telescope. And it's really bringing out the details and the craters quite nicely. And down at the bottom of the image, the bottom right, those big kind of grayish blobs down there are what are known as maria, Latin for seas. No liquid water there, we know that now, but the ancients thought there were seas there. But the middle blob, or the biggest one over on the right, is the Sea of Tranquility. And that's where we first landed on the moon just over 50 years ago. Looks like Mike's having some internet connectivity issues, and so he's going to move back inside in just a few minutes, and we can connect to his other telescope from inside his house. And that's a telescope we're going to use to look at all the other images tonight, including star clusters, galaxies, nebulae, and maybe even a comet if we get lucky, but we'll see about that. So throughout the evening, if you have any questions about any of the things we're looking at, don't hesitate either to use the raise your hand option or just unmute yourself and ask your question, and Mike and I will do our best to answer it for you. And we'll also give information about each of the objects that we're seeing tonight. So the moon tonight is about full. It's a first quarter moon. It's waxing, getting bigger. And so you can see kind of the edge where it gets black. It's called the terminator right there. And so we're just seeing half of the illuminated side of the moon tonight. There's always half of the moon illuminated and half in darkness, just like there's half of the Earth always illuminated in daytime and half in darkness. So now you can really see those three big gray blotches down at the bottom, and the center one is the Sea of Tranquility. And somewhere right near the center, I believe, of that maria is where we first landed on the moon 50 years ago. And you may have heard that NASA just announced that there'll be another moon landing with people in 4 years. So 2024, we're gonna have people back on the moon, and one of the two astronauts will be a woman. It's about time that we actually had a woman on the moon, and we only have 4 more years to wait for that. So pretty exciting news. Mike, can you hear me? Yeah,
I can, yeah. See, can you hear me now?
Yeah, we can.
Okay, I'm going to go up to the, whether you can, I'm just moving it around a little bit, as you can see, and you can see some of these, I once knew some of the names of some of these craters are quite famous, and this is a great time, you know, you see them at the Terminator like this, so they're in high contrast. Okay, I'm going to go back up to the house, and we'll switch to the 20-inch telescope. But this one, I'm just going to leave like it is. It'll continue tracking.
Sounds good. As Mike is making his transition back into the house, I wanted to bring your attention to the little dots in the center of some of those craters. There's one that's really easy to distinguish right near the center of the image of the moon. You can kind of see a little white dot in the center of a crater. And those are actually spires coming out of the center of the craters, caused by the impact of whatever big chunk of rock actually hit the moon to make those craters. If you imagine a water droplet hitting a pond, the droplet hits and then it kind of comes back up into the center. The same thing happens when a big rock hits an object like the moon. It creates a big hole, but the energy brings the material up in towards the center into kind of a pinnacle or spire. And that's what we're seeing in the center of all those craters that we see a little pockmark. So there are a couple of them that you can see quite easily tonight. And as Mike was mentioning, at this phase of the moon, a quarter phase, and a few days earlier, is the best time to really see the relief in those craters and to see those spires coming up in the center there. So I mentioned the moon is by far the closest thing we're going to look at tonight. It's a measly 240,000 miles away, which is nothing because my Subaru Outback went 310,000 miles before it died. So I could have made it out to the moon in my Subaru. Could have made it back though. So the point is the moon is really, really close compared to everything else we're going to be looking at tonight. If we could travel at the speed of light, we could make it out to the moon in just in about 1.5 light seconds. And everything else we're going to be looking at tonight is going to be light years to tens of thousands or millions of light years away, compared to just 1.5 light seconds with the moon. So 240,000 miles is the distance that light can travel in 1.5 seconds. 6 trillion miles is the distance that light can travel in 1 year, which is what we call a light year. 6 trillion miles. So we're going to be looking at stuff much, much farther than 1 light year away.
Okay,
yeah,
Samuel, I'm back up at the house.
Oh, great. Thanks, Mike. I just wanted to mention the comment that Deborah just mentioned. The International Space Station will be coming over, but I don't think we'll be able to track that and take a look at it tonight, but she's right. It is a whole lot closer than the moon. It's only about 100 miles or so up.
Okay. So as Samuel was saying, this is, we're looking at this through my 12.5-inch plane wave telescope. It's a fairly high resolution video camera that we're using. It's about 16 megapixels, and so I've made images of the moon this way by taking video using the same camera and taking hundreds of video frames and then stacking them, and you can then the detail you can see here is pretty impressive. But when you do that, the detail just becomes totally amazing. You can see way down and blow up the detail in some of these areas.
Oh, we're watching the moon.
Yeah.
Okay, so I'm going to, technically, this was going to start at 10, so maybe we want to leave the moon image there for a second longer and talk, or should we move on?
I think we're good to move on.
Okay, all right. I'm going to, interestingly, see, right now my other telescope is tracking the moon. But what would you like to start with? Now, you know, it's not really super dark yet. So,
Yeah, you know, what if we started with just a star, like Vega?
okay, yeah, and or Arcturus right out
Sure,
here.
yeah, either one I think would be great.
Okay,
Might be
so,
a nice contrast to look at both of them.
Contact.
okay.
Vega.
Hey, Sam.
We don't have our video on.
Hello, welcome.
Let's see, now I want to share my screen here.
Turn the video on.
Hey, Armin, I see you.
Yeah, we're recording. We'll get all of this up on the website tomorrow.
Okay, so this screen here is showing the what's called SkyX, which is actually what controls the telescopes. And what I just did was centered the telescope on a star called Arcturus, which is in the constellation Bootes. And so now we are going to take a short picture of that, and we'll take a look at a picture of a star. So suppose we're going to take a rather short picture here. I'm going to pin this at number 1. Take a picture, maybe. Just I got to take 4 seconds at least, anyway. All right.
So this star is relatively close. It's only about 36 or 37 light years away. Just lost your audio for some reason, Mike.
Oh, I haven't said anything in a while. That's the reason.
Okay.
Okay. Nicely centered. All right, now I'm going to share this screen so you can see what I'm doing, what I've got here. Let's see. Oh, I've got to get back to manipulating two different all these windows. Let's see here. Okay, I got to stop share, and then I got to share screen, and I'm going to share this. Okay. Okay, there it is.
There we go.
Yeah. Yeah. So that's Arcturus. Now, you know, I just spent one of the things about these telescopes is they're on a computer-controlled system. So I can, with that program SkyX, I can direct the telescope to go anywhere I want, and it points it. Now this, you'll see that this star is exactly in the center of the screen, because I just did a program that that aligns and causes this telescope so that it knows where it's pointing at. And what it does is it just points all over the sky, and it takes hundreds of pictures, well, maybe 150 pictures of the sky, figuring out where it is. Each time it takes a picture, it does what's called a sky solve, plane solve, figures out where it is, and it takes 150 of these pictures, puts it together, and develops a model of the sky, so that when in the future I want to make the telescope point somewhere, like at this star, it's able to point it exactly right. And so I think the accuracy of my pointing at the moment is on the order of less than 20 arc seconds. And now that probably doesn't mean anything to most people, but the size of the moon is about 30 arc minutes. So, you know, so this is a tiny, tiny, tiny fraction, you know, 60 times smaller than the size of the moon. So we're able to point this telescope exactly where we want it to be pointed. And that's all pretty amazing. This technology has come along in the last 10 to 15 years. And before, none of this couldn't have, all of this became very tedious in the past. You had to figure out what a star that you wanted near where you wanted to look at, and then you you worked out angles away from the star or whatever, and then tried to get close. So this system here is totally amazing, and it makes us able to do what we're doing tonight, which is do a lot of hopping around and quickly.
That's nice when
okay.
stuff works.
Yeah, it is. Yeah, and fortunately, it's working now. Unfortunately, last night, the computer that I'm using to control this telescope temporarily died on me. And so I spent some anxious moments getting the second laptop working. Fortunately, this one came back to life, and so it's working again. Let's try something a little more interesting this time. If we point, let's see, away from the horizon, maybe point east, we can see something.
Yeah, the Ring Nebula should be in the east. That should be a good one.
Yeah, okay, let's try that. So that's 57, right?
Yeah, and as Mike is going to that object, so the star we were just looking at, what you couldn't see is that it actually has kind of an orangish tint to it. All the objects we're going to see tonight are black and white, but Arcturus is one of the orange giant stars in the sky, meaning that it's nearing the end of its existence. Not quite as close as Betelgeuse, which is a red supergiant, but it's on its way there. And so you can actually see the orangish tint of Arcturus when we see it just naked eye in the sky. Now we're going into the constellation Lyra to see this this next object called the Ring Nebula. And the brightest star in Lyra is Vega, which is a blue supergiant star. And so we won't be able to see that color tonight, but when you look up in the sky and see Vega, it almost has a bluish tint to it. And that's because it's a much, much hotter star than Arcturus. The younger stars that appear bluish are the hottest, whereas the cooler stars that have run the course of their existence, like Arcturus or Betelgeuse, have an orangish or reddish tint to them. We made it over to the Ring Nebula, Mike?
I think so. And so now I'm going to try to take a picture of it. And so we'll anyway change the settings of the camera. Go out to maybe 10 seconds, and we'll see what happens here. Let's
So this object we're about to see, the Ring Nebula, is basically the remnants of a sun-like star that's run out of fuel and cast its outer layers out into space. All sun-like stars will do this eventually when they run out of fuel, and we've got about 4 billion years left, 3 to 4 billion, until this happens to our star. So we're about to see what our solar system will look like in roughly 3 to 4 billion years.
and there it is.
Yeah, nice.
Yeah, and if you look closely, now my interconnection is unstable. Let's see if I zoom in here a little bit more. We've had a clearer nights before. So that's 100%. Well, 100% was better. Yeah, if you look very closely there, you can almost see a white dot in the middle here. And that is the actual remnant of the star, the corpse of the star that created this Ring Nebula, and it's called a white dwarf. And yeah, so that turned out pretty well.
Yeah, that's really nice. Yeah, so
this is one of the things you can actually see reasonably well through an eyepiece. Yeah, this is one of the fun things to see, because you can actually see a nebula with the structure in the nebula through an eyepiece. So this is fun. But we're doing it through a camera right now. Yeah, this telescope, I should maybe, if I describe what's going on at the moment. This is a 20-inch telescope. The last one was a 12.5. This is a 20-inch telescope. And the camera is a black and white. That's why Samuel was saying you can't see the color in that previous picture. But I do take color pictures with this camera. And you want to say, how can you do that with a black and white camera? And what you do is you take a lot of different pictures through different filters. And so I have red, so we're taking pictures right now through a clear filter. So we're just getting a black and white image. But I can take pictures through red, green, and blue filters as well and create a color image by assembling separate pictures taken through different color filters and making a color image. And so those of you who've seen my color pictures, that's how they're made, even though I'm taking them with a black and white camera.
Thanks for that explanation, Mike. That was great. So this object, even though it looks like a little smoke ring, is actually an hourglass shape. We just happen to be seeing it from our perspective on Earth with a top-down view. So we're just looking down at one end of the hourglass. And so we see the outer ring of one side. If we could rotate this object 90 degrees, we could actually see more or less the hourglass shape. And we'll actually take a look at an object like that a little bit later on tonight. I think it's still too close to the horizon for us to see, but there's another planetary nebula roughly in the same part of the sky, but just like I say, a little bit lower down on the east, called the Dumbbell Nebula. It's roughly the same size, just turned at 90 degrees. You can actually see the dumbbell or the hourglass shape. But to kind of put this object in perspective in terms of size, that little ring you're seeing right there is about a light year in diameter. So 6 trillion miles across, which means that you could easily fit the entire solar system inside that little smoke ring. It wouldn't even be a snug fit. It would be easy to fit it in there. And this is also a pretty close object to us. I think this one is just over about 2,400, 2,500 light years away, which in the long scheme of things is pretty close.
Right.
I don't know, it might be worth trying to see if M27 is up high enough. It'd be kind of cool to have that one back to back.
Yeah, we can give it a shot.
I think it's still too low. I think we're going to have to wait a little bit, but you never know.
Well, I can try it because we're on the right side of the right side of the telescope is pointing in the right direction right now. So let's try.
Let's give it a shot. And then we had a request for the double in Lyra.
Okay, let's try M27 find. I see it there. Let's see if the telescope will point there. Well, it's going to go there.
Great. Yeah, should be really nice.
Okay, there it is. All right, now go back to the screen share. You can now see me operate the camera. So there are different screens here, different programs that operate different things. The program that SkyX operates the mount that points the camera. This is the points the telescope. This is the control system that actually controls the camera. So I am going to now take a picture of that, 10 seconds long, and actually we can try, well, we'll try 10 seconds. I can always go to 20 seconds. This camera, by the way, is a black and white camera, but it's also, it doesn't look like a conventional camera. It's a black box, actually. No, we're not seeing anything here. No, that's not good. I could try 20 seconds.
Yeah, I mean, it's a little more diffuse than the Ring Nebula, but not much.
Yeah, I should be able to see it, though. Let's see what's going on. Let's try 20 seconds. Telescope is pointing correctly, so we should be able to see it, get to it, but I'm seeing stars. So that means I'm not, the observatory isn't blocking it. So,
Yeah.
bit of haze. Well, I
Maybe
think we'll
that's
try. I think we'll try this one a little later then.
okay. Yeah, you want to try for the double double Epsilon Lyra?
Oh, I see. Give me a number.
Oh, okay. Yeah, hold on. I'll get you the. You don't need.
Double.
You need altitude and azimuth, or
Well, if you have, if there's an NGC or a IC or reference for it, I can do that.
oh, okay. Yeah. What is the catalog number for that? Give me 1 second. I think I can figure that out.
While we're in that territory, let me just try to look for M51.
Yeah, I mean that should be good.
Yeah, why don't we just do that, and while you figure that out, I'm going to move there. This telescope's going to swing around. Yeah, I could stop share, screen share. So you're now seeing the screen that shows the telescope arriving at the object that I just referred to as M51, which is a galaxy. So that's this is a horse of a totally different color, as they say. All right, let's try this one now. I'm going to go back to my taking a 20-second picture of this object. Oh. Huh. I see it there. Let's see. I'm in manual mode. I got to change this mode there to medium. There we go. All right.
There we go.
Yeah, it's yeah. Let's just leave it that way. Yeah, it's not totally dark yet. Really dark. So we're seeing this haze we're seeing around here is just due to the fact that it's not pitch black out yet. But you're seeing the galaxy pretty well. You know, that was the problem, I think, Samuel, with that previous picture.
Yeah, I was just gonna say that.
I didn't have the screen. I didn't have the screen stretch set right. You might just want to go right. Well, we'll go back to it. But there it is. So I can even.
Yeah, we can talk a little bit about this one before we go back to.
Yeah. Right.
M27.
Yeah. So this is a very famous. This is if you're a. Okay, I'm going to reduce a little bit of this haze here by changing. There we go. That's a little nicer. Yeah. So this is an iconic galaxy. This is a galaxy much, like the Milky Way in the sense that it's a galaxy. It's a combination of billions of stars that have that were once formed, and then they in the same general area, and they got gravitationally attracted and created a structure called a galaxy. And this galaxy is iconic because of its beautiful shape. You can see the main part of the galaxy right here, and this other little arm out here. Now, this other arm is actually another galaxy, and this one is rotating around this galaxy. And in fact, if you look carefully, you'll see that this galaxy is stretched out in this direction. It's not quite round. It's actually pulled out in this direction. And because of the gravitational pull of this, eventually these two galaxies are going to collide and become a single galaxy. And a lot of that's going around. We live in a galaxy group called the local group, which is not very clever name, but about 30 galaxies. The nearest galaxy to the Milky Way is called the Andromeda, and that galaxy is actually bigger than the Milky Way. It's a couple of 100,000 light years, but in about 4 billion years, we're going to collide with it. And it's going to get very close and eventually merge with the Milky Way. Now, to give you a perspective on the distance, though, we're looking back here we're looking back in time about 25 million years, because the light that left this galaxy left that galaxy 25 million years. And so, as astronomers say, this is the distance here is 25 million light years away. But I think to most people, it makes more sense to say the light left there 25 million years ago, which means there's a look back time. You're looking at this thing as it existed 25 million years ago. So that in a sense is pretty amazing.
Indeed it is.
They collided?
They aren't collided, they haven't collided yet, but they're on their way.
Yeah, I mean, they're probably getting closer than what we see them in this image, right? Because they've been merging for another 25 million years since we got this shot.
Yeah. That's the thing about galaxies. 100 years ago, the collected wisdom, well, there were, I mustn't say the collected wisdom, but there were several different camps. But in general, most people thought everything that in the universe was in this cloud that we now call the Milky Way. And it was only because of some work that was done by a woman called Henrietta Leavitt, who came up with a method of measuring the distance in the sky at large distances, that we were able to figure out how far some of these things really were. And Hubble in the 20s used the method using something called Cepheid variable stars, and used that method to actually measure distance for the first time to distant objects. And he discovered that things that were called previously nebula were actually galaxies like this one that were much further away, like the Andromeda, which I think was one of the first ones that he figured out was not just thousands of light years, but was millions of light years away. And all of a sudden, the whole perspective on what were thought of as the universe 100 years ago totally changed.
Yeah, before Hubble, basically the Milky Way was the entire universe. And then the universe got a whole lot bigger after that.
And it continues to get bigger.
That's right.
Yeah, this is one of probably the more impressive objects we'll see tonight. This thing. It's one of my favorites, and I have a famous picture. I have a very nice picture of this that's currently hanging in the library in Jackson Hole Gallery. Unfortunately, no one can get into that library because it's closed. But at some point, it's going to open, and those pictures will still be there. And in fact, one of my pictures that's in that library just won an award on Wikipedia. I just found out that it won an award of the 5 best science pictures of the year. And it's a picture of the South Pole of Jupiter. And so I won a similar award 3 years ago for a picture of the eclipse. Well, anyway, so that's nice. So maybe in a couple of months, people will be able to go into the library and see that picture. Anyway.
Should we try to go back to the Dumbbell Nebula and take a look at that?
Let's see. We're actually close to another one in this area. Maybe we should try 101.
Sure.
Yeah, since we're very close to it. Here's another one that's in the same group as this one. Galaxies tend to be in clumps, and this is a galaxy that's M101. Okay, I'm gonna show you the whole story here. I'm gonna do share screen. Okay, so this, back to the SkyX screen, and you can see here it says M51. So that's what the telescope is pointing at. Now I'm going to ask it to find M101. You see how close it is? M101 was just a hop, skip, and a jump from M51. It's about the same distance away. It's not quite as spectacular, but I think we'll see it. It's now 10:30, so it's gotten darker outside, and the moon probably is getting lower, so we're not going to blur it out too much. So now I'm going to tell the telescope to go there. I'm clicking this button, and it says, "Do you really want to go there?" And I said, "Yeah." And okay, so now you can see the telescope slewed there. Didn't have to go very far, and so I'm going to go back to my other screen over here. So I haven't done one of these Zoom things too recently, so I'm screwing this up a little bit, so I apologize for the time. Okay, so we're back at the camera screen again, and now we're going to take a 20-second picture of M101, which is a sister galaxy of this one. Yep, there it is. Okay, so I'm going to do medium here, and so this is also what's also nice about this one is called the well, it's called the Triangulum Galaxy, but it's also sometimes referred to as the Samuel?
Pinwheel.
What's that?
The pinwheel.
Whirlpool, not the whirlpool, but the
pinwheel.
Pinwheel. There's two pinwheel galaxies. This one is sometimes referred to the pinwheel, but the shape is very, suggestive of a pinwheel. And what's interesting about both of these two, M51 and M101, is that they're face on. Not all galaxies are face on, and we'll see some. I think we'll look at some that aren't face on, but this one, you can see the arms are quite pretty, and they're fairly symmetrical, as you can see. These bright objects, like here. Well, I should say something about these galaxies, and this is a good one to look at. All the bright stars that we see here are not in this galaxy. They're in the Milky Way. We're looking through the Milky Way to this galaxy. But these areas like this here, this here, these are objects that are in that galaxy. Now, this galaxy is also about 25 million light years away. Again, light left there 25 million years ago. But what these are bright areas. In a color picture, these would actually look reddish. And these are areas where stars are forming. So these are probably huge star clusters in this particular these galaxies, and there are areas where gas is congregated very in close distances, and the gas is compressed, and new stars are formed. So that's how all stars are formed, is in nebula, and they congregate because they're gravitationally attractive, forming these large galaxies.
Mike, I'm not sure if everyone sees the image exactly like I'm seeing it, but when you had adjusted the contrast a little bit differently, I was able to see a bit more detail.
Okay, let me change the contrast some.
Yeah, right there.
Is that better?
Yeah. I don't know if everyone's seeing the same thing I'm seeing, but that looks a little better to me.
Yeah, these are the arms. This is a very bright group of stars that are not stars, but they're clusters of stars that are being formed.
Yeah, it looks like other people are seeing better detail now as well.
Okay, good. Yeah, let me know, because I can adjust it manually.
Fantastic. Should we try for the Dumbbell Nebula?
Okay, let's go there. All right, so I'm going to stop share here. I'll go back to this screen. Okay, so we're going to M27. Find way over here. See it? So now I'm going to tell the telescope to go there, and it's going to go there. It's going to actually pass over the North Pole first, and which is doing right now. Okay. Okay, it's there. See, it says tracking. So now the telescope is tracking that object. Now we're going to share a different screen. We'll go back to the camera screen. I'm getting a little faster at this so I can do it more quickly. And I'll take another picture.
So just as a reminder, this is another one of these planetary nebula, the remains of a sun-like star. And this one we're going to see a side view of instead of top down. So instead of seeing a ring like the Ring Nebula, we should see kind of a dumbbell shape or an hourglass.
There it is.
Yeah.
Okay, and I can, let me change the contrast a little bit. How does that look to you?
That looks good.
Okay, yeah, I can, let me,
Yeah, definitely better before.
yeah. Yeah, so this is, as Samuel was saying, this is a planetary nebula. This is the future of the the sun is going to form something like this when it burns through all of its hydrogen, which is still burning. Then it's going to, once all the hydrogen in the core is gone, the star is going to momentarily cool off. Then gravity will take over and compress what the remaining gas, and it turns out it's going to compress the what's left after the hydrogen is, in fact, the sun makes its energy by converting hydrogen into helium. And in the process of doing that, there's some leftover energy equals mc squared. Well, not all of the mass, there's less mass in the helium than there was in the hydrogen. And as a result of that, the difference in the mass is energy. And that's what gives the sun its light and heat. Well, once it crunches, loses all of its hydrogen, it crunches the helium, and it turns out the helium will get hot enough to actually start another nuclear reaction, and it'll convert, the helium will be made into carbon. But once all the helium is gone, it'll get cooler again, the sun will compress, but it won't get hot enough to heat the carbon hot enough to make another nuclear reaction. And the sun will become a dead star, and the gas that was remaining will float away and create an object like this, like what you're seeing here. The dumbbell that Samuel was talking about is not totally visible tonight. We do have some, part of this haze here has to do with the fact that there's a moon out. But there's a shape, there's a curve here, and there's a curve over here. And it kind of has a dumbbell shape. And that's what gives this thing, this shape here is what gives it its name, a dumbbell.
Yeah, it looks pretty good.
Yeah.
So I've got the right ascension and declination for the double-double.
Okay.
It's right in the neighborhood.
Right in the neighborhood. All right. So we'll, I have to, I'm going to stop this share. I'm going to go back to go back to this window. Okay. So now I have to go into, tools and go into slew of coordinates, and you're going to tell me what they are.
Yeah,
All
the
right.
right ascension is 18 hours.
1-8. Oh, sorry. 1-8 space. Go ahead.
44 minutes
44 space
and 20 seconds.
20. All right.
Declination is 39,
39 space
40 minutes
40 space
and 12 seconds.
12 seconds. Okay.
And
Now
that's
I'm
gonna,
say,
I was gonna say that's gonna center us on one of the two sets of the double-double.
okay.
At least it should.
Okay. Okay, well, the telescope is moving. I'm gonna change the, all right, well, there it is. It's already arrived.
Yeah,
And as you say, it's very close to Vega.
yeah, it's in the right spot.
All right, so that's good. We'll close this out. Now we'll go back to the camera screen.
Yeah, probably just the minimum exposure time. It's magnitude 4.5.
So this is a biggie. All right. Okay, so we'll yeah, well, maybe we'll go to binning 1 and maybe down to 4 seconds and take a picture. All right, let's see. I've got to get this thing to. Oh, all right.
There are
Well,
two of them.
Yeah, and if I go to 5 or 6 seconds, I think maybe we'll get rid of those lines.
Great.
Now, there's an artifact, but there they are. So okay, tell me what we're looking at, Samuel.
Yeah, so this is a famous set of two double stars. So it's known as the
Okay.
double-double. One of the sought after treasures of amateur astronomers who really like splitting double stars. So you have to have a pretty good telescope and a really nice eyepiece in order to split the double-double, because these stars that are in orbit around one another are actually pretty close together. In reality, they're about 0.16 light years apart, which is pretty close. And in the sky, they're only separated by a couple of arc seconds. So they're really, really fast, really, really close together. Mike was talking about arc seconds earlier. There are 60 arc minutes in a degree and 60 arc seconds in an arc minute. So 3,600 arc seconds in 1 degree, 180 degrees over the entire dome of the sky. And we're just talking about 2 arc seconds in separation. So what we're seeing here is that Mike's got a really good telescope and a good camera attached to it, so we can actually see that small separation. There are actually 2 sets of double stars right next to each other. With Mike's camera and telescope setup is probably a little bit too small to get both sets of the double-double next to each other. So we're just seeing one set.
Okay, so what we're seeing what would without this magnification would look to most as the single star.
That's right. All 4 stars look like a single star to the naked eye. I think with the telescope, probably around 8 inches, you can separate 2 of the stars. So it looks like you can see 2 stars. But we're actually separating all 4, and we're just seeing 2 of the 4 stars that make up the double-double here.
Okay.
Yeah, so that's pretty cool. And the other set is just a few about a dozen or so arc seconds away. But it's going to look exactly the same as this one. They're about the same separation as this pair is.
Yeah, but not in the same field of view. Yeah.
Yeah, I think just off the field of view. But yeah, there are some amateur astronomers who will spend all night seeing how many double stars they can split. And this is one of the gold standards. if you can split the double-double, you're doing pretty good.
Okay. Yeah, well, we're having no trouble doing it with this telescope.
Congratulations, Blake.
Yeah. Okay.
All right, well, we've seen a couple galaxies. We've seen a couple planetary nebula, few stars. I thought we'd do a globular cluster. How about
All right.
M13?
M13, that's a winner.
Yeah.
All right. Okay, so we're gonna getting faster at this. Go back to the screen. Okay, so now we're gonna enter in M13. I'm gonna change the scale here. Fine, there it is. All right, it's actually, we don't have to flop the telescope. Okay, I will get into that, but it goes right, it'll go right there very quickly. So, okay, we're there. Now we'll stop share, share. Okay, now we're going to change things again. We have a dimmer object. Give it 10 seconds. Yeah, some of these things you can see quite well through an eyepiece. And this is one of the objects that's fun to look at through an eyepiece. The galaxies I'm showing that we looked at so far, you can see a lot better through with this what we're seeing here. You can't really see the detail through an eyepiece of these galaxies until you get to a huge telescope. But so here we are. Yeah, this is M13. This is probably the most famous. It's called the Great Hercules Globular Star Cluster, and it's globular because there could be as many as 1 million stars here. And so you all know that we're all what's called stardust. All the elements are made from stars, and all the stars are made in clouds of gas and dust that are gravitationally that become gravitationally unstable. The gas and dust gets denser and denser and denser until it reaches 15 million degrees Kelvin, and then a nuclear reaction happens and it converts hydrogen into helium, and a star is created. Typically, though, not one star is created in a cloud of gas and dust, and typically you get a cluster. Now, nowadays, and our sun was undoubtedly in a cluster, but not one like this, because we wouldn't exist if we were in a star cluster like this. These are ancient. These things probably are over 10 billion years old. Now, this cluster exists in our Milky Way galaxy, but the stars in this cluster are probably even older than the galaxy itself. They go back 10 billion years. And the reason why our sun, or we wouldn't exist in a cluster like this, the stars are too close and they interact with each other, and the environment that would allow life, a solar system of ours to exist, would not happen here, because the other stars around it are too close and they would mess it all up and it wouldn't happen. So what happened to our sun, we were probably formed in what's called an open cluster, and eventually in the 4 or so revolutions that the Milky Way, for objects like ours, like we are, where we are in the Milky Way, it takes 250 million years to go totally around the Milky Way. Now, we've probably gone around several times. In that process, our sun got split off from whatever other stars it was created with. Well, but then there are these things that are antiques that exist, and they're very beautiful. And these are one of the things that really are nice to see through an eyepiece. Now, this one is interesting. You can see there's some shapes here. Now, there are colors to these stars too if you take a color picture. But what you can see here very clearly, there's an X marks the spot. See the X here? So X mark, that's the center. And there's a gazillion stars that we're not being able to see here in the center.
Might be able to bring a couple of them out with a longer exposure if you want to try.
Or a shorter exposure.
Yeah, just binning. Yep, you could do that too.
I'm binning. Let's see, what did I bin this at 4? So let's bin it at 1 and take a shorter exposure. And we'll lose the stuff at the outer edge, but we might be able to see a little more detail in the center. I'll do a 4-second exposure of and see what happens. All right, so now I gotta change that. Now zoom in here a bit.
I think you can see that X a little bit better now.
Yeah. You notice the stars are not pinpricks. The problem here is our atmosphere. This telescope maybe it's possible I could focus it a little better tonight, but even when it's perfectly focused, you still can't see these stars as pinpricks because the atmosphere blurs them. That's why the Hubble telescope is able to get such outstanding views because it's above our atmosphere. But yeah, so now you can see that X shape is very clear here. Yeah.
I can't remember if we mentioned the distance to this galaxy. I think Mike, or galaxy, globular cluster. I think Mike mentioned that it's these globular clusters occur in the upper and lower halos of big galaxies, not in the plane of the galaxy. I think this one's about 25,000 light years away. So almost as far as you can get seeing something and still be inside the Milky Way from our perspective.
Yeah, so this is not, as Samuel was saying, this is not in the plane. The galaxy has this basic plane, but then if you've seen sort of drawings of, well, you see these other galaxies, they tend to have, particularly ones that aren't edge on, there's a glow above the middle. And that's where this galaxy, this star cluster is. It's in the central bulge called a halo in the center part. And the 25,000 light year, 25,000 light years is about the same distance that our sun is away from the center of the Milky Way too. So anyway, it gives you a little, so we're a quarter way across our own galaxy.
Maybe we can do the Sombrero Galaxy now to show people what the disk looks like in that central bulge.
Yeah, that would be a good one. All right, so we'll stop sharing here. We'll go to share screen, go back to here. Okay, so here's M13. Now we're going to, this is in the southern sky, so this is going to be a bit south from us. Yeah, this is in a, the astronomers have worked out a system of latitude and longitude. And right now we're looking at a latitude of 36 degrees, which is kind of, you know, pointing almost not quite 40 degrees up from the horizontal here. But we're going to start looking at things. This one is going to be way down lower than this. So this is M104, if I'm not mistaken.
Yeah, I think that's right.
And there it is over there. Now we're going to hit this magic button and tell the telescope to go there. And it is, yeah, so this type of telescope, you see, it can't go directly there. It's going to have to go over here and come all the way around, but it won't take that long. This telescope is doing what is now called a flop. It's flopping from the telescope has two orientations. It's either on the east side looking west or the west side looking east. Now it's going to be on the east side looking west. It was on the west side looking east. Now it's backward. Now it's going back to the other side. And we're doing this cool flop. All right, so we're down there. Stop sharing this screen. Go back to the camera screen. All right, so now we're going to take, this is going to be a dimmer object. I'm going to change the exposure parameters here. And I'll go 20 seconds. That line that we are seeing there could easily be a satellite line that went right through our picture. Okay. Okay, there it is. Okay, now I'm going to rotate this so it looks, edit, rotate, right. And we'll zoom in a little bit. So there it is.
That's nice.
Yeah, yeah, it's called, so this is called the Sombrero Galaxy. Guess why?
You can really see the disk nicely tonight and the bulge.
Yeah, so this is there are all sorts of, I think there are graphic art. This appears in various forms of graphic art that this shape. I've seen it in this, what's that, Armin?
Flying saucer?
Flying saucer, yeah, right.
That would have been another good name for this galaxy.
Yeah, the saucer. Yeah, yeah, yeah. I forgot how far away this one is. This is not also in our local group, so this is a ways away too.
Yeah, I think this one is over 40 million light years away. Let me see if I can find out exactly here. I can't remember off the top of my head, but I want to say 43 million. Let's see.
So that would make it the farthest distant object we'll have seen tonight.
Yeah, that's definitely true.
And you know, that means if, let's say it was 40 million light years away, which means we're looking at it like it was 40 million years ago. And what was going on Earth 40 million years ago? Well, I got to tell you that humans like we are didn't exist then.
The reference I found says actually just 30 million. So still the far,
Okay.
but not quite as far.
Yeah, long way away.
You interested in trying to do those elliptical galaxies in the Virgo cluster that we did last time?
Yeah, we could do that.
I know they don't look like much, but I think it's so cool just to see the galaxy where we took the first picture of a black hole last year.
Okay. All right.
Let's see, that's M87.
All right, M87. Yeah, that's the famous picture that I'm sure everybody has seen of that was taken with radio telescopes that were spaced out all over the entire Earth so that we could get the resolution to do that. Okay, so here it is. We're going to find it. Not very far away, so that's good. Hit, go.
And this one is farther than the last galaxy we looked at. This one is over 50 million light years away.
Yeah, I've taken pictures of a galaxy that was that far away, and ones that were in the distance that were 500 million light years away. So that's about as far object as I've ever photographed in my pictures. Now that's an interesting number too. So to see in a galaxy that is 500 million light years away, or when you think back at what was going on Earth 500 million years ago, well, that was when the very first life that was really exploding, not the very first life, but when life on Earth really was exploding, 500 million. So we were looking at an object that the light left at that point and just arrived to us now. Okay, so here we are. Now we're going to go back and take a look. So this won't look quite as interesting from a standpoint of a picture, but this is in a cluster of galaxies called the Virgo cluster.
Yeah, so very different type of galaxy than what we've seen so far. So far we've seen spiral galaxies, either face on or edge on. Now we're going to look at an elliptical galaxy, which is more like just a big blob of stars in an oval shape without any articulated arms.
Yeah. And
I think if we adjust the contrast,
yeah.
should be able to see the extended disk. It's close there for a second.
Yeah, sort of.
Yeah, so that's just the very core of the galaxy we're seeing, and then there are a couple other galaxies scattered around it.
Yeah, it kind of looks like a bright star, but it isn't.
And so in the center of that galaxy
is the moon is just a little too bright tonight to. Yeah, I can't. Try to. I think going larger is going to help this.
But I mean, we can see that it's not a pinprick of light. It's not a point source. It's an extended disk of light. And
yeah.
So in the center of that huge collection of stars is a supermassive black hole. Trying to remember the actual mass of that black hole. It's several tens of millions of solar masses. Let me see if I can find the exact number here. But an absolutely huge black hole that we call a supermassive black hole. And as Mike was mentioning, the very first picture that was taken of a black hole was taken of that one last year by the Event Horizon Telescope. And there are also really interesting pictures of this galaxy taken by the Hubble Space Telescope and other telescopes that look in both radio waves and X-rays. And you can see this enormous jet coming out of this galaxy. And it's a jet that's actually formed by all the stuff falling into the black hole. And apparently these jets are pretty common. It's not stuff coming out of the black hole, that doesn't happen, but caused by the infall of material into the black hole. And we see these jets and other supermassive black holes all over the universe.
Yeah, let's see.
There's another object that we might be able to see now that we're in Virgo, Mike, that's quite a bit farther away and kind of stays on the theme of galaxies with large black holes. The closest quasar is actually in Virgo, 3C273, and I've got the declination and right ascension for it if you want to try. It's going to be a tiny little pinprick of light, but it's by far the most distant object that we can see with size telescope that you have or that I've ever used.
Okay.
Let me know when you're ready.
I'm ready.
So right ascension, 12 hours, 29 minutes, 6.7 seconds. And declination, 2 degrees, 3 minutes, 9 seconds. And it's apparent magnitude 13, so exposure time shouldn't be a problem.
Yeah, as you say, it was very close. I can see that. All right, so now I'm going to have the telescope to go there. Oh, wait a second, I screwed it up. Hold on. Yeah, it was 12 hours, right? 29, that was it. Yeah, okay.
Yeah, 12 hours, 29 minutes, 6.7 seconds.
Yeah, okay, got it. Yeah, okay. All right, now I just go back to the camera. All right.
So this object is much more farther away than the last galaxy we just looked at. This one is a whopping 2.4 billion light years away. So 2.5 billion years ago, that really was the beginning of life on Earth.
Yeah. Now the question is.
Yeah, so I'm looking at a picture of the star field online. And give me 1 sec. I can tell us which star it is. Okay, it's this guy right here. I don't know if you can see my cursor. So Mike, there are those two fairly bright stars. Yep, and now go down to the left, the next brightest one. Down. That bright one right there, that's it.
All right, wow, okay.
Yeah, that's Quasar 3C273.
So I remember the discussion we were having about quasars. So this is an object that, as far as, you know, there was a lot of controversy in the 70s about these things, and that these things were so bright, no one could believe they were that far away because they were so bloody bright, that they could be actually tens of billions of light years away. So, and this is, you said this was 2 billion light years away.
Yeah, 2.4 billion. So yeah, we're seeing that when life first started on Earth. Or to put it in another way, if we were on a planet orbiting that quasar right now, if we took a picture of Earth, we'd see Earth when life just started.
Yeah, if we could see it, because Earth wouldn't be very visible, but yeah.
If we could see it.
Yeah.
Assuming pretty good technology.
Yeah.
How far is the edge of the universe? 4.5?
No, it's the farthest objects that we were once able to see that are about 46 billion light years away. There's no edge to the universe, but the objects that once were that we were once within our horizon have moved that far, so they're that far away now. Because the things that we've now seen haven't stayed where they are. They've moved, so further away.
Yeah, and that's just the radius. The diameter of the known universe is 93 billion light years across.
Yeah.
And getting bigger all the time, as Mike mentioned.
Yeah. Okay. You know, the moon is still out. You wanna go back to that and see what it looks like?
Yeah, just in case folks didn't see it earlier.
Yeah.
So now from the farthest object all the way back to the closest. I like it.
Yeah. All right. Okay. So now let me figure out how I'm going to do that. That's the other Michael Adler. Let's see. How do I do that? Okay, I got to stop sharing this screen for sure. And I see, yeah.
We just got another request, Mike, for M61. There's a
yeah, I might have to do that. Okay, I'm going to take a quick ride.
You're going to go down. You headed down to the observatory?
Oh, well, I haven't gone yet, but you want to look at something else?
Well, we can do the moon. We also just got a request for M61. That's the galaxy where there's a supernova right now. I don't know if we'll be able to see the supernova, but we can try.
Well, that's very close to where we were, so that's no, that's easy. All right.
So while we're headed over here, we had a question about how the universe can be 93 or 96 billion light years across when it's only 13.84 billion years old. It's a great question. Oh, yeah, there's the galaxy. We'll get back to that question in a second. Let me see if I can find an old picture of that galaxy, and so we can figure out which point of light is the supernova, if it's visible. Let's see here. It's not the image that I need. Okay. Let's see here. Might need to change the contrast a little bit, Mike. I've got a picture of other direction. There we go. Yeah, actually, that might be really good. Let's see if I can find an image.
What's interesting about this picture, I have to, let's see, move this screen down. I just want to point out something else too. There's another galaxy here, you see? So we were looking at this larger one here, but that's another one right there. I have no idea what number it is, but when you look at these galaxy pictures, you often see lots of other galaxies too. And that's another one right there.
All right. So, oh yeah, the supernova is supposedly it's that second really bright star up at the very top on the left. That one.
That one right there.
Yeah.
Wow. Yeah, and people know that these things are supernovas because they weren't there before. They're there now, and then they disappear.
Yeah. So that one went off on May 8th.
Wow.
Or at least we saw it go off on May 8th. The distance to M61 is, let's see.
Yeah, while we're doing this one, I'm actually taking pictures of M63, which is actually a very pretty, I might try to look at that one.
Okay.
That's also not too far away. That's up higher in the sky, be away from the moon further.
So it's 52.5 million light years away. So that supernova actually exploded about 52.5 million years ago on May 8th.
Huh. Wow. Yeah. So it's just it's a supernova that we're just now seeing that just happened to explode 52 million years ago.
That's right.
That's kind of mind-boggling. All right. Okay. So here's a picture of actually it'll be a larger galaxy than this one. It's called the Sunflower Galaxy. I'm actually taking a picture of this one. It's one of the ones I've been working on. Sometime in the next month or two, I'll send a picture of this one out. There it is.
Oh, that's
Yeah.
beautiful.
Yeah, we haven't looked at this one. We should have. This is a nice one. Yeah, it's called the sunflower because of its shape. You know, you can just see the various objects or the little petals in the part of the flower.
The detail was actually quite a bit better at the very beginning, Mike. Before.
Yeah, let me just do it the way it was. Yeah.
Yeah. It's a tiny bit overexposed in the center, but we really see the detail in the arms there.
Yeah.
I think those are called flocculent spirals, right?
Could be. Yeah, that's too bad. Medium. Yeah, the challenge in taking pictures of things like this is that it's like a lot of even some terrestrial stuff where parts of the image you're looking at here, like the center part of the galaxy, is way brighter than the edge parts, but you want to get a picture that shows it all. So it becomes a challenge. So there's a couple of ways you have to deal with that. One way is you have to reduce the exposure so you don't blow out the detail in the center part. And that means you've got to take a zillion pictures. So each picture can't be brighter than that would blow out the detail of the brightest part. But then to see the dimmer parts, you've got to take a zillion pictures and then add them all up and stack them together. So that's where you take astronomical pictures. It's you take one picture properly exposed for the brightest, and then you take a lot of other pictures to get the detail in the dimmer parts. Or you can take separate pictures at different exposures and combine them, kind of like HDR you do on terrestrial pictures. And I've done both of those things. Okay, I'm going to, I think we probably have done it with the big telescope. This might be the end of the night. I'm going to go down to my observatory. I have to use a headlamp now, and see if I can get see if I can let those of you who haven't looked at the moon. This is with my 12.5-inch telescope and with a video camera taking the picture.
So as Mike is headed down there, I can get back to that question about how the universe can be so many more light years across as the total age of the universe. So the conundrum is that, you know, if the universe is only 13.84 billion years old, traveling at the speed of light, stuff could only have traveled 13.84 billion light years. So it seems. But there are a couple things that change that. The first is that over the history of the universe, there have been times where the universe has expanded much, much faster than the speed of light. So during the early epochs of the universe, and during the period of inflation, the universe itself expanded much faster than the speed of light. And space and time can do that. It's just that anything with mass isn't allowed to travel faster than the speed of light. But space-time can do that without any problem. So the expansion rate of the universe was greater than the speed of light early on. It's since slowed down to below the speed of light, but is accelerating again. So that's a big piece of the puzzle. Even though there has only been 13.84 billion years of time for light from objects to reach us, That's the visible universe that we can actually see. There's been plenty of time for the universe itself to get much, much larger than 13.84 billion light years in radius. And so everything has been expanding away from us since the beginning of the universe. In fact, everything has been expanding away from everything else that wasn't gravitationally bound. And when we see something 13.84 billion light years away, or let's say a little bit closer, say we're looking at a quasar that we see today 12 billion light years away from us, it's actually much, much farther away than that, because it's been expanding away for at least 10 billion years or so since it formed. And so even though the light that we can see can only travel from 13.84 billion light years away, the full time that the universe has existed, the universe itself can be much, much larger than that, because its expansion has exceeded the speed of light.
How did they make the determination that it was 93?
Yeah, that's a great question. I don't remember the details of that right now. But it has to do with the estimated rate of expansion of the universe at different times, and the rate of expansion that we're seeing now, the overall energy density of the universe, and this new mysterious force that we call dark energy, which seems to be accelerating the expansion. So when you take into account the best theory we have about the inflationary period of the universe, the rate of expansion that's changed over the existence of the universe as a whole, and the current acceleration that we're seeing in the universe because of dark energy, and the energy density of the universe, how much mass there is, when you factor all that together, you come up with an estimated size of 93 billion light years in diameter. But diameter really doesn't describe the shape of the universe. It's not a sphere because there's no edge. We think our universe is at least 4-dimensional. And so it's what Einstein called a 3-sphere. It's a 4-dimensional sphere. The human mind can't really create a model of what that looks like in 3D, because we only experience 3 dimensions, but there are probably at least 4 spatial dimensions, if not more than that. So that's why you can have a universe that's finite in size, but has no edge.
Wow, thank you.
Yeah. Have you made it down there, Mike? Looks like you're muted in the observer. There you go.
Okay, can you see? Can you see my screen?
We can't see the moon screen yet. You might have to unshare.
Because I'm sharing. Maybe I have to unshare the other one.
Yeah.
Okay. I'll leave this screen where it is.
I think I might be able to do it for you. Let's see here if I can do it. I got it for you. Now we can see it.
Can you hear me, by the way?
Yeah, we can hear you, Mike. And I was just able to toggle the screens from my computer, so now we can see the moon.
Okay, cool. Yeah, so we're getting another good view, still a very nice view of it. I once knew the name of these craters. They're very famous, these 3 here, but anyway.
Yeah, I can't claim to know the names of them either.
I'm sitting here looking up at the moon with my eye, and I'm looking down here at the screen, and I'm seeing this incredible detail of the moon. That's kind of cool.
Mike, it sounds like that even though I can see your screen, it might be that other people might not be able to see it.
Yeah, that's correct.
Sounds like that's correct. So even though I was able to toggle and see it, I think you might have to unshare your screen from the house before.
Go up. Yeah. Let's see.
Sam, can you revoke his screen sharing on his other computer since you're the host?
I might be able to. Then I don't know if I'd be able to reshare them though.
Well, I can go up and stay here anyway, whether I'm. Yeah.
You guys still can't see the moon though, even though I can, huh?
If you go up to the view options, you can scroll down to Mike's second screen and see the moon.
And that's what I'm doing. And so I can see Mike's second screen right now from my computer. I'm not sure why you guys can't see it.
I can now.
Oh, you can now?
Yeah.
Everyone has to go up to the second view option themselves.
Ah, I
Right.
see. Yeah, so if you guys didn't get that, if you you go up to view options at the very top of your screen, there'll be two different screens from Mike Adler. One of them connected to the 20-inch telescope and one connected to the 12.5. And if you toggle between those two, you should be able to see the moon in one of them.
Okay, I'm back up here.
We figured it out, Mike.
Can you see it now?
We can, yeah.
Okay, there you go. Well, I'm actually up at the house. I can't move the picture now, but there it is. I was just saying when I was down there, I was looking out at the moon in a tiny little spot in the sky, and then here it is in incredible detail. Yeah, so this is a video camera. It's about 16 megapixels. So we're seeing it in great detail. I actually last night, I'm going to make an image of the moon I took last night. What I'm doing is I'm taking actual videos, 200 frames plus of this, and then stacking taking the video apart and making individual pictures out of it, and then stacking them together. And what happens when you do that is that the blurring in the atmosphere sort of cancels out because it's always different. And the thing that stays the same is the actual detail on the moon. And so you can get incredible detail and much more than we're seeing here, but this is pretty impressive as it is.
Any last questions that anybody has about any of the stuff that we've seen tonight before we wrap things up?
Yeah, by the way, I'll mention it, but if those of you who are here like what you're seeing, this is a free program, but anyone who wants to donate to Wyoming Stargazing, this is not it's a not-for-profit, but there are funds that we take to run the operation, and so donations are always welcome.
Thanks, Mike. I appreciate you mentioning that. And yeah, as he said, donations are certainly appreciated, and we'd also appreciate it if you spread the word. We'd love to get people, all over the world connected to our virtual stargazing. So please spread the word widely, and we hope to see you back here next time. As the summer progresses, there'll be different objects to see in the sky, and hopefully we'll be able to show you some cool stuff.
Yeah, as the summer goes on and we see the summer Milky Way, there's all sorts of beautiful nebula in the summer Milky Way that are just incredible. So we're getting closer to that all the time. Right now, we're in this sort of galaxy season where we're looking away from the Milky Way and we're looking at other galaxies. But once the summer happens and we get into all the nebula are in our own galaxy. And so as we get into nebula season, we'll be able to see a lot of different objects as the summer goes on. I've had a lot of fun doing this, by the way. This has been fun. Getting the 12-inch telescope with a video camera working like this, and then also doing the 20-inch telescope. So I'm using 2 out of 3 of my telescopes here.
Nice.
Mike,
And we should probably make it easy for you to donate. All you have to do is to go to wyomingstargazing.org, and you can click on the donate button on the homepage. Go ahead, Armin.
I got a question for Mike. Mike, which galaxy is this one?
Which galaxy is which one? You're looking at the moon here.
No, he's got it up on his. Looks like M51 to me.
Oh, I see. I have to look at your picture. Let's see. Where are you? I will see. Oh, there it is. That's M51. That's the one we were looking at earlier, Armin.
Right, that's what I wanted to know. Thank you.
Yeah, that was the Whirlpool Galaxy.
Great. Nice show, Mike. Thanks very much.
I'm glad you came. I'm glad you're enjoying it. Armin was my first boss when I first started working at GE 1,000 years.
We go back, I think, 1970 or something like that.
That's right. I started working at GE in 1971.
That's pretty cool. Thanks so much for joining us, Armin.
You're welcome, and thank you for the fine lessons you gave us this evening, Sam. We appreciate it.
Yeah, my pleasure. And thanks to everyone for being here. Wouldn't be virtual stargazing without all of you, so we really appreciate you giving up your Thursday evening to be with us, and hope to see you again sometime.
Thanks, Mike and Sam. Good night.
Good night.
Yeah, by the way, I think you've you're actually recorded this. So
I did, yeah.
Yeah, so it'll be up on the website at some point. And if you want to share it with other people.
I will. Night, everybody.
Good night.
Night.